So this is the second video of examples of solving integrals by the method of partial fractions. This method works when you're trying to integrate a rational function like the one I have here, where the numerator and denominator are polynomials on x. So the idea is to factor the denominator and try to write this expression that I have as the sum of two terms. The problem in this one is that I really don't have two terms. If I want to factor this denominator, it really is x plus 1 times x plus 1. So if I write two factors like this, it's not going to work because I'm going to have, my goal is to write it like somebody over one factor and another term. And that wouldn't make any sense because if they have the same denominator, there's no algebra involved in doing that. So how does this work in this case? Well, in this case, we think of it like I could have added two terms, one of them over the denominator x plus 1 and another one over the denominator x plus 1 squared, and still having the denominator, the common number for these two terms would have been x plus 1 squared, which was x plus 1. Which is x squared plus 2x plus 1. So when you have a repeated factor, or a factor with multiplicity in the denominator, then this is the technique you need to think about. We need to consider the two parts we're multiplying, the two parts that we're adding. One of them has denominator x plus 1, and the other one has x plus 1 squared. So if I do that, then to get the same denominator, which is x plus 1 squared, all I had to do was multiply a times of x plus 1, and the b is already over x plus 1 squared, so that was not multiplied by anything. Correct. So that way, I would have gotten this. If I got that, if by adding two terms like that, I got my original expression, then that means that ax plus a plus b was 3x plus 2. So at this point, I can ignore the denominators, and all I'm doing is writing the numerator. So, and then at this point, we compare coefficients. So a is the coefficient of x, so it has to be a is 3. And my other term is a plus b is the constant term, should be 2. So I have a very simple system. If I write the system of equations, it's just a is 3, and a plus b is 2. So at this point, the system of equations is very simple because my first equation gives me the value of a. If you plug it in the second equation, you really get 3 plus b is 2, so b is negative 1. So this means that the integral I wanted to solve, the 3x plus 2 x squared plus 2x plus 1, can be rewritten as a, which was 3, over the factor x plus 1, and then minus 1 over the factor x plus 1 squared. And now each of these integrals, I could solve them easily. So I have to solve this integral, and I need to solve this integral. So for the first one, it's just 1 over u du, right? If I do a little mini substitution, so this means that this is 3 natural log of the absolute value of x plus 1. And for the second one, I might have to do a little bit more than that. I had to do a little u substitution again, because in this case, u would be x plus 1, and the du is dx. But I have u to the negative 2 when I'm integrating. And the integral would be u to the negative 1 divided by negative 1. Right? Because you add the 1 to the exponent. So my integral for the second term turns out to be, so I'm not going to write explicitly the substitution. It's negative from this negative. But then I'm going to have x plus 1 to the negative 1 divided by negative 1. I'm going to leave it like that so you see what happens. I'm going to erase this. So those two negatives combined, I get 3 natural log of absolute value of x plus 1 plus 1 over x plus 1 plus a constant. Okay? So that's this example. If you have a term, a denominator that's squared, you have to consider still two terms in the sum. One of them when it's raised to the first power, and another one when it's raised to the second power. Okay, and my next example is going to be a little bit trickier, because on this one, what I want to notice is that the denominator is a cubic now. Now, this is not going to be a typical problem if an instructor gives you a cubic and the denominator probably going to be simple as this one where you can factor it, or it's going to be of quadratic, easily multiplied by your x, so one of the factors is an x, or to practice, they can just give you the factors in the denominator. But in this case, I made it so that we could factor. If you think about the denominator, x cubed plus 2x squared plus x plus 2, the first two terms have a factor of x squared. But if I do that, then this looks like the factor over here. I can write it like that. My next two terms just have a factor of 1 in front of them and have the common factor of x plus 2. So this really is x squared plus 1 times x plus 2. So I found a way to factor this cubic. Now, something I didn't emphasize before is that this works if the power or the degree of the numerator is smaller than the degree of the denominator. I said that in the first video, but we should check that first. If not, we should first divide. Do a long division and find out to write it as the polynomial part plus a remainder, and that remainder is the one that will have a smaller degree in the power, smaller degree in the numerator, and we'll still have to repeat this process. But in this case, we do have the power of the numerator smaller, so we're fine. So if I keep working on my method, if I write 2x squared plus 3x plus 8 divided by x cubed plus 2x squared plus x plus 2, I found out that the denominator could be written as, so I'm going to write here, somebody is over x squared plus 1, and somebody is over x plus 2. Now, I wrote this on purpose like that, but this is going to be not the correct way to figure to set this up, because my numerators in this case don't have to be constants. In this case, it is constant because it has to be lower than the denominator. So if the denominator is power 1, the numerator should have power 0. But on the second one, if the denominator is power 2, the numerator should have power of 1. So this is not the correct way to set this up. I should have here ax, so let me erase this. I should have here ax plus b, and that way this part still has a lower degree than the denominator, so I have a c term over here of x plus 2. So now I'm going to have 3 variables. Okay? So now this is different from the past examples. Okay, so now if I work this out, we have to be doing ax plus b times the x plus 2 plus the c times the x squared plus 1. I'm writing everything under the same denominator. So I would have to do those multiplications to put them under the same denominator. So on the left side, this is my numerator, and I'm going to write the denominator as I found factored. So at this point, I can ignore the denominators and just work with the top. So if you work this out, I get ax squared plus 2ax plus bx plus 2b Now with the next term I get cx squared plus c. And over here I'm going to leave the 2x squared plus 3x plus 8. So I have all these terms. And now what we need to do, I want to compare coefficients. This method is called undetermined coefficients. So I want to factor everything that's multiplied by x squared. I have a and a c. So a plus c multiplied by x squared. Now I'm going to see who is multiplying the x. I have a 2a and a b. So the 2a plus b is multiplying the x. And now the terms that are not marked are just linear terms, constant terms, 2b plus c. So I'm comparing that coefficient, each coefficient to the coefficient on this side, which means that a plus c should be 2, 2a plus b should be 3, and my last one, 2b plus c should be 8. So now I have 3 variables, right? So I have 3 variables and I have 3 equations. So let me write those down here. Let me put this down here in red. So my first equation was a, since I have 3 variables, I'm going to leave a space for the b here. So a plus c should be 2. My second equation is 2a plus b should be 3. And my third equation is 2b plus c should be 8. So I need to find a way to solve this system equation of 3 equations with 3 variables. And there are several ways to do this. I'm going to realize that the first and the third have c's. I can do it for the middle, second, and third, but the first and the third have c's. And I'm going to eliminate c from those two. Okay, so from the first equation and the third equation, I'm going to eliminate the c. So if I multiply the first one by -1 and I add it to the third one, the c would cancel, right? So if I do that, I'm going to multiply it right here. I have a -a minus c equals -2. I'm going to copy the third equation, which is 2b plus c equals 8. If you add them, I get, if I add them, I get -a plus 2b equals 6. How am I going to use that one? Well, I haven't used this middle equation here. And that's great because from the first and third, I eliminated the c, which means my equation has a's and b's, but this middle equation has a's and b's. So there we go. If I copy it down here, oops, sorry, wrong pen. If I copy it down here, I'm going to have 2a plus b equals 3. I have this new system that I need to solve. This is my new system that I need to solve for a and for b. So I need a lot of space here. So let me start putting some things on the side. This is how I factored it. I'm going to put it over here. This is the work to get my partial fractions. I'm going to put it over here. I'm going to leave this big, but I'm going to put it over there. Okay, so this new system, I can solve it if I, for example, multiply the first equation by 2, right? If I multiply the first equation by 2, I get -2a minus 4b equals -12. You have 2a, sorry, I multiplied by +2, not by -2, so this stays positive and this stays positive. I don't have to change the sign. The second equation is a +2a plus a b equals 3. So when I add them, the e's cancel, and I get 5b equals to 15, so b is 3. Great. Knowing that b is 3, I can use any of the equations to get my other variables. For example, I can just use this one, and knowing that b is 3, 2a plus 3 should be 3, which means that a is 0, right? 2a is 0, so a is 0. So I got a b, I got my a, I'm only missing c. And I can get c, say, from this equation. Sorry, from the first equation, right? The first equation says as a plus c is 0, sorry, a plus c is 2. I found that a was 0, so c is 2. And I got all my 3 coefficients. So a is 0, b is 3, and c is 2. So we got it. Now let me shrink this. Put it on the side, and let's solve the integral. So the integral I wanted to find, I found that I can rewrite it as the integral of a x plus b, but a is 0, so I just need the 3 over x squared plus 1 plus c, which was 2 over x plus 2. So I'm following the pattern from here. Right, you have to look who is the a. The a was the term divided by x squared plus 1. Sorry, the b, ax plus b. So a was 0, and the c is the numerator of x plus 2. So this is the integral I'm trying to solve now, which is pretty simple, because this becomes 3 times the integral of 1 over x squared plus 1, and this becomes 2 times the integral of 1 over x plus 2. This, recall that this is exactly the derivative of the tangent inverse of x. This is 3 times the tangent inverse of x. And this, what we did before, is a natural log of x plus 2. Okay, so this is a more complicated example of solving an integral by partial fractions.